I couldn't stop recording. So it only stopped recording when you guys finally left. So it was nice seeing you chat and question where had Sir disappeared to. I wasn't sure whether I could put that video up. What do you ladies say? Is it okay if we put it up?
No.
No, you don't want that up. Okay, we'll get started. I think you can see my board behind, right?
Yes. Yes, sir.
Okay, great. So what we're going to be doing is working through questions on paper 1, but we're going to just first of all do one or two things, and then we will be able to do those questions. So we gave you some basic knowledge yesterday, and let's just test something and see whether you still remember it. Okay, suppose I've got a sphere of 30 coulombs, right? Plus, and I've got 2 more identical spheres. Okay. Now, suppose that I touch, and this is 0 and 0, and I bring them all together. Okay. And then I separate them. How many of you think you know what the charge is going to be on each of them? Any ideas?
At the end, sir, when I separate the...
Okay, just don't say. I just want to see. Put a hand up if you think you know at the end what each of the 3 are going to be. If you think you know. So we start with 1 of 30, 0, 0, touch them all, separate, separate, separate. Okay, so Jay knows. Does anybody else know? Jade, what do you say it's going to be?
I think they're each going to be 10, sir.
Each going to be?
10 coulombs.
Exactly. Would you like to explain why, Jade?
Because from my knowledge, you add the 30 plus the 2 zeros, and then you divide by 3.
Exactly. So you bring the 30 together, then the 10 go on each of them. They get spread equally. And then when you separate, it's plus 10 plus, or 10 plus, and 10 plus. Okay, super. Then, if that's easy enough, I just want to show you what they're going to ask us to do. They're going to put them like this. They love playing with 3 charges. And they're going to ask you what's the force on the middle one. So if they're each 10 plus, first of all, that's plus, that's plus. What is the force on this one going to be from that one? Is it going to be up or down? Who thinks they know? Just put up a hand. This one, by this one, will it be pushed down or pulled up? Like charges do what?
Repel.
So is it going to, who says it's going to go up? Who says it's going to go down, the force? You're right, all 3 of you. So this one gets repelled down. We don't have to worry about that one. That one will get repelled up. Okay, who can say this one's 10 plus, that's 10 plus? Who knows what this one's going to do to that one? Is it going to pull it or push it? Who says it's going to go left? Who says the force of this one on this one is left? And who says the force of this one on this one is right? So these are like charges do what? They
Repel.
repel. So that's going to be repel. That one's going to repel that one. So our force is going to be left. Ah, nice, Ezra, joining us. Thank you. Lovely. Nice to see you. Then we've got two forces, and they vector addition. Do you remember how to do vector addition? So vector addition, we just do this, and there's going to be our resultant. So that's what they're going to ask you to do in the problem. All happy? Okay. So let me share with you or present with you okay, now have a look at this. Not that, this. Okay, watch this video. Hey, no man, skip the advert. Okay, watch this. Okay, so what did you think of that? What did you think of that? Like magic, the way you rub that balloon and it pulls water. Water's heavy, but it pulls it. I wanted you to see that. Okay, let's try going to look at our questions. Okay, wait, let me just start present again. Present now, entire screen. Okay, let's have a look at our worksheet. So there's Coulomb's law. And then adding a few fields, etc. Okay, let's go to 1.7. Two charges of 2 nanocoulombs and minus 2 nanocoulombs are located on a straight line, S and T, are 2 points that lie on the same straight line as shown in the diagram below. Which one of the following correctly represents the direction of the resultant electric fields at S and at T? Okay, so which direction does a field go? Does it go from positive to negative or negative to positive? So what we do is we put a little positive here, and we ask ourselves, is that positive attracted or repelled by that? Is that positive attracted or repelled by that? And it's obvious that it's going to go like this. So this one is to the right. Now we put a positive here. And we ask ourselves, that positive, is it attracted or repelled? And the answer is positive is attracted to negative. So it's going to go to the left. So at S, it's pulled to the right. So we want an answer with right. And at T, it's pulled to the left. So we got right and left. So the answer must be A. Right, let's go on to the next one. They all end with a 17. Okay, the magnitude of an electric field, a distance r from a point charge is E. the magnitude of the electric field at a distance 2r from the same point charge will be. Okay. I'm just going to go back here. Someone's got a squeaky microphone. I'm just, Ezra, you're the main suspect. I just want to see if that solves the problem. Okay, that seems to solve the problem. Just forgive me for muting you, but it's just stopped that squeaking. The rest of you, I hope, can hear me. Or no, I muted you all. Oh, we'll just have to put hands up. Forgive me, but it stopped that squeakiness. Okay, how was that problem? Was it all right? Easy enough? Okay. So now the next problem is something's got a force of, let's just quickly have a look at it again. The magnitude of an electric field, the distance r from a point charge is E. The magnitude of the electric field at a distance 2r from the same point charge will be a quarter, a half, 2, or 4. Okay, so they've got a charge. Let me just get a different color. Let's get blue. Okay, and that charge is, doesn't matter if it's positive or negative. So now you've got an electric field here, and then that's the distance r, and then you've got an electric field 2r. Okay, so this distance is r, and this would be 2r. Okay, so what do you guys think the answer will be? Any ideas? Well, let's get the formula for electric field. It's a similar one to this one. And here's the formula. Electric field equals KQ over R squared. Okay. Now, first of all, if you move it twice the distance, will it be bigger or smaller, the electric field strength? Who says it will be bigger? When you move it from here, from there to there, will the electric field get bigger or smaller? Who says bigger? Hands up. Bigger field? Stronger field? Who says weaker? A weaker field? Hands up. Okay. Now, this is how you can do it. Look, the further you go away from Earth, the weaker the gravity comes. So the answer is going to be weaker. But how much weaker? Okay, let's show you how you do it. This is what you do. Make each of those 1 for the first case. So let's say E1 is going to be electric field number 1 is going to be KQ, and when the distance here is R. So what is the answer? Now, this is just a quick and dirty way of figuring it out, but because they don't want you to give the answer. They just want you, they don't want you to show working. So just make K1 times Q is 1, R is 1, and it's all squared, and that comes to 1 times 1 upon 1 times 1, and that all comes to 1. So your electric field has got a strength of 1. Now, this is case number 2. Case number 2. We got KQ over 2R. 2R squared. Why? Because there was R. This is twice the distance. See what I've done? Mm. But nothing has changed except the distance is doubled. K is still 1, Q is still 1, 2R squared. Now, here's the only trick. Do we square the 2 and the R? Who says we have to square the 2 and the r? Yeah. So think of it as in brackets. Over 2 squared times r1 squared. So when you square 2 times r, you've got to multiply it, the 2 squared and the r squared. So the answer is going to be 1 upon a quarter, because 2 squared is 4 times 1. So what has happened to the electrical field strength? It's become a quarter when the distance became twice. Do you guys get what I said? Is that easy enough? Is that okay? Okay. So the answer to that one is going to be a quarter. I've unmuted you, and that squeaking has stopped. Okay, that's great. So let's go back to preview. So the answer is going to be this answer here, a quarter. Let's go to 227 or 1.27. Two identical positive charge spheres which are free to move are placed near each other on a frictionless surface. Okay, there's a frictionless surface. There's a sphere. There's a sphere, and they're both positive. Come on. Okay, so they're both positive. So now my question is, what is going to happen? Do they attract or repel?
Repel.
Lovely. Well done. So they're going to move apart. Oh, don't be silly there. So they're going to move apart. Now, will they move apart faster and faster? Will they go, as they go further apart, what happens to the field? Does it get stronger or weaker?
Weaker.
Lovely. So at first it's pushing like crazy, and then it pushes less and less and less and less and less and less and less. Okay, so they will move away from each other, but with increasing or decreasing acceleration. Who says decreasing? Yeah, because as they get further apart, they get weaker, the force gets weaker. So that must be the answer. They can't move with constant acceleration because the field is getting weaker, and they don't move away from each other with zero acceleration, because if you have a force acting on an object with no friction, it causes acceleration. Okay, easy enough, 1.27. Let's go to the next one, 1.37. Two charge spheres of magnitude 2q and q, respectively, are placed a distance r apart on insulating stand. So there's 2q, and there's q, and they are placed a distance r apart. If the sphere of charge q experiences a force of F to the east, then the sphere of 2q will experience a force of... Now, come on, I want to see you guys. Didn't we do that yesterday? What did we say that you mustn't be tricked by? Who can give it to me in a Newton law? Newton number?
3.
Well done. And so what are you going to do? You're going to go Newton 3 says that for every action, there's an equal and opposite reaction. So they're going to push each other with the same force. I said, don't be caught by them. So these guys are cunning. So if there's a force to the east, then there's going to be a force to the west. P, Q, and R are three charged spheres. When P, Q are brought near each other, they experience an attractive force. When Q and R are brought near each other, they experience a repulsive force. Oh no. Which one of the following is true? Oh dear. This is like an IQ test. This really is like an IQ test. Okay, so there's P and there's Q. And they are brought near each other. They're attracted to each other. Okay, so we know that P and Q have what? The same sign or different signs?
Different.
Yeah, different signs. Then when P and Q are attracted to each other, so the one is positive and the other is negative. When Q and when Q and R, okay, here's R, are brought together. When Q and R brought, they experience a repulsive force. Okay, so what do we know about Q and R?
They're the same sign.
Same sign. Okay, same sign, different sign. Which one of the following is true? P and R have the same, P and R have charges with the same sign. Let's just think about it.
No. No.
So those are repulsive.
B.
So these are the same, those two, but these two are different. Okay, well, anyway, different. So P and R have the same sign.
No. No.
Who says no? Everyone? So those two are different. Say that one is positive. Then that one would be negative, and then that one would have to be negative as well. P and R have the same sign. No. P and R have charges with opposite signs. Is that correct?
Yeah.
Looks like that one. P, Q, and R have charges with the same sign. No. P, Q, and R have equal charges. Well, we don't know that. So then the answer must be B.
B.
Okay, so one just has to draw it out. I think the magnitude of the electric field at a point P from a positive charge is Q. Which one of the following statements below represents this electric field is correct? A 1 coulomb charge placed at P will experience a force of magnitude X newtons directed away from Q. The magnitude of an electric field at point P from a positive charge Q. Okay, so there is Q. And here is point P. And the magnitude of electric field at point P from positive charge Q is X. Okay, so this is now equal to X, is the strength. Okay, Which of the following statements below regarding the electric field is correct? A 1 Coulomb charge placed at P will experience a force of magnitude X newtons away from Q. A 1 Coulomb charge placed at P will experience a force of magnitude X newtons directed away from Q. Okay, well, if it's a positive charge, it will be directed away. A force of positive 2 Newton charge placed at P will have a magnitude of a quarter X. No, it's going to be bigger. A positive 1 Coulomb charge placed at P will experience a force of magnitude X towards Q. No, if it's a positive charge, it's going to be away. The force on a 2 Coulomb charge placed at P will have a magnitude a quarter X. No, that doesn't, it's got to be bigger. It should be 4X. So which of these looks correct to you? Well, okay, let's look at them again. This is possibly correct. I don't see any reason why that shouldn't be wrong. A force of 2 coulombs charge placed at P will have a magnitude of a quarter X. Now, why would it be less? This one here, a 1 Coulomb charge will experience a force of magnitude towards. No, if it's positive, it should be away. This is definitely wrong. That looks definitely wrong. A force of plus 2 coulombs placed at P, 2 coulombs. Why would the magnitude be smaller? It should be 4 times bigger. Or twice as big, should I say. Not a quarter. So these three look definitely wrong. I'm left with A, but what do you guys think? Can you see something that I'm not seeing there? Does it look like it has to be A? What do you say? I think it must be A. I just don't know why they say a 1 Coulomb charge at P will experience a force of magnitude X directed away from. That's the one that looks the most correct. The others look definitely wrong. Okay, 1.57 must be that. Okay, two charges plus Q and minus Q are placed at distance D. Plus Q minus Q are placed at distance D from a negative charge there. The charges plus Q and minus Q are located along lines that are perpendicular. Which one of the following arrows correctly shows the direction of the net force on charge minus Q? Okay, that's positive, that's negative. In which direction is this going to be pulled? Up or down?
Down.
Negative, positive. Negative,
Yeah,
positive.
down.
That's going to be pulling it up, right?
Oh.
Makes sense? Now look at this one. Negative, 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 negative. Is it going to be pushed to the left or to the right? By Q. Yeah.
Right.
Okay, negative. What do like charges do? They
So.
repel. So would you like to change your opinion?
Left.
Left. So now we've got two forces. We've got two forces, one up and one to the left. So what's the resultant of those two going to be? Is it going to be that one, that one, that one, or that one?
C.
Yeah,
C.
it's going to be C. Okay. That one was a nice, easy one. Okay, look at this one. two charged particles are placed a distance r apart. The electrostatic force exerted by one charged particle on the other is F force E. Which one of the following graphs shows correctly represents the relationship between the electrostatic force and the square of the distance r squared between the two charges? Oh no. Ouch. Which one of the following graphs below correctly represents the relationship between the electrostatic forces? Force, what's the relationship between force and r squared? Okay, force and r squared. Ladies, I need your advice. How are we going to do that one?
Between
Any ideas how we would do it? Well, what is the relationship between force and R? It's an inverse relationship. And it's an inverse squared relationship between force and R squared. So it's as R gets a little bit bigger, force gets a lot smaller. Look at this. Let's just show you. Okay, we're going to use this force equals KQ1 Q2 over R squared. Force R squared. Okay, let's make each of those 1. Okay, so if R is 1, this is going to be 1 times 1 times 1 over 1 squared. What is force going to be equal to?
1.
1. And what is R squared going to be equal to?
1.
1. 1 squared, right, is 1. Okay. Now, what if R is 2? What if R is now 2? It's going to be 1 times 1 times 1 over 2 squared, which is, so let's make R 2. What is R squared going to be equal to?
2. 4.
4. And what is force going to be equal to?
A quarter.
A quarter. And let's just do it one more time. If R is 3, then that's 3 squared is going to be 9. And force is going to be equal to 1/9. But what kind of relationship is that? It's as the 1 gets smaller, this gets, as F gets smaller, R squared gets increasingly bigger. So I wonder which of those graphs shows that. Let's just go and have a look again. As R squared gets bigger.
G or B? I don't know.
As R squared gets increasingly bigger, F gets lots smaller. So as that gets bigger, you say D.
B.
B. So as R squared gets bigger, okay, when R squared is 9, F becomes 1/9. That looks about right. And when R is 1, F is 1.
Wait.
No, but that doesn't look right, does it? So, but that looks correct. When r squared gets bigger, f gets smaller.
B. I think it is B.
It has to be. Do you guys think it has to be B?
Yes.
And then what about this one? When r squared is 1,
But that doesn't make R 0 when R is 0 at least.
Hmm.
okay, so when r, we can't have it as r 0 that give us a divide by naught error. I'm just wondering
Yeah.
if it's that relationship. Do you know what? You know what I want to do? I really want to try plotting it. Okay, because I'm a little confused. So I'm just going to, I am a little bit confused. I just want to go back to here. And I'm going to stop presenting just so I can draw on the board for a second. Okay. So this is r squared and this is f. Okay. So let's have our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Naught, naught, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. When f is 1, r squared is 1. When f is a quarter, r squared is 1, 2, 3, 4. And when r squared is 9, that is 1/9. So it does seem to be, but now I'm still not no closer to what that's what the graph looks like. Which of those graphs look like that? Okay, what is going to happen when, let's make r squared equal to, let's try a half. Okay, that's a half. So then what is r going to be equal to? What's a half squared? A half squared is equal to a quarter. And then what is f going to be? If this is 1 upon a quarter. Okay, grab a calculator, just type 1 times 1 times 1, that's 1 over 1 quarter squared. And you'll find that the answer is 4. Right? Am I correct? It's 4.
Yes, sir.
So when r squared gets very small, this becomes bigger, like 1, 2, 3, 4. So the graph is like that, yeah. That's the graph. So it's to go back to it, and I just worked it out by placing values in for r. But it was this part of the curve that was worrying me. And so it's obviously, it's what do they call that? They call that not a hyperbola, or what's the name of that in mathematical terms?
Exponential.
Exponential.
Okay, exponential. So we were right. 1.77. Do you guys want to see the board again? Let me just stop Let me just, or I think you can still see the board. Yeah, you guys can still see the board. Okay, let's go back to 1.77. We've done that one. Okay, let's go on. 1.87. Three identical positive charges, Q1, Q2, and Q3, are initially situated on a smooth flat table as the corners of the right-handed triangle. The diagram below shows the charges as viewed from above. Positive, positive, positive. Which one of the following diagrams shows the direction in which Q2, they always use the middle one, will move as a result of the electrostatic forces exerted by Q1 on Q3? Okay, I want you ladies to look at it and tell me what's the answer going to be. A, B, C, or D?
C.
C. Everyone agree it's C?
Mm-hmm.
Yay! Because this one is pushing down and this one is pushing right, and the resultant of those two is going to be C. Okay. Two identical light graphite-coated spheres, P1 and P2, are suspended using identical thin isolated threads. P1 is charged, but P2 is neutral. The spheres are then brought into contact with each other as shown in diagram 1. Thereafter, the spheres assume the position as shown there. Okay, so originally P1 and P2, P1 was charged and P2 was neutral. So, which one of the following statements concerning the charge on the spheres possibly explains why the spheres moved apart after touching, as shown in diagram 2? The sign of the charge on P1, the sign of the charge on P2. Okay, could they be unequal? Who says the charges on P1 and P2 can be unequal? Who says they're equal? What did we say? When you touch two spheres, they always end up sharing the charge. So the answer must be C or D, because they are equal. And then if they repelling each other, is the one positive and the other negative, or both of them positive?
Both of them positive.
There we go. If this is past exams, look how easy they are. Okay, the magnitude of the electrostatic force on charge Q1 to another charge Q2 is F. Both charges are now doubled without changing the distance between them. The magnitude of the new electrostatic force on Q1 will be, okay, both charges are doubled. Will the force become a half, twice as much, 4 times as much, or 6 times as much? Who says that the force will get less? Who says the force will become twice? Who says the force will become 4? Who says the force will become 6? I haven't heard much so far. Okay, so what are you guys going to do? This is what you're going to do. You're going to say case 1, Q, K, Q over R squared. Okay? What are you going to do for case 1? You're going to make them all equal to 1, right? And so it's going to be 1 times 1 times 1 over 1 squared, and the answer is going to be 1. Okay? So That's what you agreed. Now, case 2. So this is F1. F2 is going to be K, but now there's 2 times Q1. The charge is going to be twice as big. 2 Q1.
Hmm.
2 Q2 over R squared. Because Q is twice as big. So it's going to be, if Q, it's going to be twice as big as Q1, twice as big as Q2. And that comes to 2 times 2 is 4, is the answer. So do you see how we worked it out? It's 4 times bigger. Okay, guys, I want to give you a problem. Do you see how that works? Okay.
Yes.
Okay, let me really test you. Okay. Here's case number 1. Now, in case number 2, R becomes a half the distance. The Q1, the one charge becomes 3 times bigger, and the other charge, Q2, becomes a third. Okay, so I'm changing everything. Here was our original case, but now the distance becomes a half. Charge number 1 becomes 3 times bigger. And charge number 2 becomes, no, that's too easy. Let's make that one equal to 2 times bigger. Q2 is 2 times bigger. Can you tell me what happens to F?
It becomes 24. If I'm not mistaken. 24, sir.
You guys are so good, eh? Who got 24?
Me.
Okay, one of you. But now, how did we do that?
Because I took 1 times 3 times 2 divided by a half squared.
You said 1 times 3 times 2 divided by a half
Squared.
squared. And a half squared is 4, which when you invert it becomes 4 on top. 1 upon a quarter. So then the 4 goes to the top. It's 1 times 3 times 2 times 4. 3, 2 is a 6, 4 is a 24. And the answer is 24 times bigger. Happy with that?
Yes.
So if you see how the method works, you can do it with any changes. You just plug in values and then you get your answer. Okay, so we use that same system each time. Let's have a look again. So if the magnitude of the charges due to another charge is F, both charges are now doubled, it must become 4. Okay, 2 small identical metal spheres on insulated stands each carry charge minus Q and plus 3Q respectively. When the centers of the spheres are a distance d apart, the spheres exert an electrostatic force F on each other. The spheres are now made to touch and are brought back to the same position as before. The magnitude of the electrostatic force when the spheres now exert on each other in terms of F is... Okay, first of all, you got minus Q and plus 3. So what is the answer of the 2 together going to be? It's going to be minus 1 plus 3. Touch them together, what is it going to become?
2.
Mm.
It's going to be plus 2. Move them apart. Each one is going to be now
+1.
plus 1. Okay, plus 1 each. So now if we imagine that this is going to be plus 1 and plus 1, what do you think is going to be the force? How is it going to change? Well, this new force, that is like still stayed the same. But this one has become 1/3, right? This is just now, that one is now just plus 1. Plus 1. And that one's plus 1. So all that has changed is that charge has become 1/3. So case number 2 is 1/3 of the charge. So which of those answers looks like it's going to be the correct answer? Who just shout it out? This one here is plus 1. Okay, so this one's charge has gone from -1 to +1. This one has gone from 3 to 1. So in other words, this one is now 1/3 of the original one. So look, don't you see what the answer is going to be?
B.
Must be B. There we go. B. Everyone see why? Because this new answer is 1/3 of the original. That one hasn't changed. So we could say it's equal to K, Q1, which is still 1, times 1/3 of the original. If that was the original, it's now 1 upon 3, 1/3 of the original. So it must be 1/3 of the force. I hope that's clear. Okay. 3 charged spheres, X, Y, and Z, supported by insulating threads of equal length, hang from a beam as shown in the diagram below. Sphere X is negatively charged. Sphere X attracts sphere Y. The Y must be positively charged. Sphere X attracts sphere Y but repels Z. So Z must be negatively charged to repel it. Okay, so which one of the following conclusions is correct? Sphere Y is positively charged and sphere Z is negatively charged. Yeah, okay, we don't even have to go further. That's the answer. Easy. Okay, particle P has charge Q and particle R 2Q. They are separated by a small distance R. Which one of the statements below about the electrostatic forces Fp and between P and R, which P exerts on R and FRP, which R exerts on P, is correct? FPR equals a half, equal to 2, equal to minus. Okay, so what is the answer? Okay, so what is the answer, ladies?
B, sir.
Okay, are the forces equal? What would you say? Are the forces equal?
No. Yes.
Aren't,
No.
aren't the forces between
Yes.
Newton 3? Newton 3
Yes.
says they,
Equal.
but are they in the same direction or are they in opposite directions? Are the forces equal but opposite directions?
Yes.
Yeah, so I actually think D is the correct answer. The forces are equal but opposite directions, so it must be D. So that's something I actually hadn't thought about, but the sign there represents the direction of the forces, and it doesn't matter what kind of what you're going to have, they're always going to be, yeah, they're always going to be in opposite directions, even if they attract in opposite directions or if they repel in opposite directions. So the answer is D. Glad I did this one. Okay, two identical spheres. This will be our last one. R and S on insulated stands carrying charges of plus Q and minus Q, respectively, are placed a distance apart. Sphere R exerts an electrostatic force of magnitude F on sphere S. The two spheres are now brought into contact and returned to their original positions. The magnitude of the electrostatic force that sphere R exerts on sphere S is now. Okay, who thinks they know the answer? Who says it's A? What
B.
What happens if we what happens if we
It's B.
what happens if we touch a negative charge to a positive charge? Plus one, minus one. Plus one, minus one. It's going to be equal to, yeah, it's going to be plus one on Q minus one on S, that is going to be equal to 0, divided by 2 is still equal to 0. So the answer must be 0. Got no force exerted on each other anymore. I hope that makes sense.
Yes.
So now, ladies, what do you think? Do you think electrostatics is a nice section?
Yes.
Yes.
It kind of helps to go over this because, did you see how we solve a lot of the problems by just substituting in our own numbers? Even in this case where I had to draw a graph, that had me stumped for a while. So I had to draw this last little part of the graph to see, it's doing that. So what do you guys spend the rest of your day doing? Can you go out and do exercise?
I was exercising this morning in my room.
Ezra, did you exercise this morning? Every morning?
Yes.
And
no, I just started. I'm lazy,
so what did you do? Go out for a run?
I ran and then I exercised more.
Lovely. And the rest of you, what did you spend your mornings doing? Listening to music? Doing exercise? Cooking? Sewing? Baking? Anyone bake?
Me.
Tidying your room? No.
No.
Thank you so much for being here. Are there any questions regarding any of this work? Perhaps just finish the rest and then if you've got questions. But you see, it's a lovely, easy section. It makes up for some of the other ones. Now, you know what I'm thinking of doing tomorrow, if you ladies are willing, and I want to do rates of reaction, Le Chatelier and KC, and that little table which has start, use up, end. It's like the toughest section. So I thought I'd like to try that on Thursday and Friday, finish it on Friday. It's called Rates of Reaction, Le Chatelier, and it's got that little start, use, produce, end, and concentration. It's a really awful question. That's in paper 2. And so I thought Okay, we've done something nice. I'm getting a bit tired of physics. Let's try a bit of this really awful chemistry. And we'll do last year's question on that section. We'll just dive in at the deep end and we'll see how it goes. So thank you so much for being here. And
Thank you, sir.
Thank you, sir.
okay, thank you. So anyone want to chat to each other before we log off? Well, I suppose I can log off. You can carry on chatting. Okay. Where do I log off? Okay. Cheers.
Bye, guys.
Bye.